Thanks for having me. I will be presenting the YOLO-NAS, recently published SOTA object detection model created by Deci.ai, and why you should care. So a word about me. I'm working as a computer vision engineer for more than a decade. I participated in writing a bunch of the open source libraries and got my Kaggle Grandmaster badge, which I'm doing in my free time. And currently I work as the maintainer of the Super Gradients. This is open source package for the training deep learning models. More on this later. And actually how we released the YOLO-NAS and why. So Deci as a company is a young startup which are doing end-to-end deep learning development platform. And as a core business, we provide ways to optimize the model and to find architecture that is efficient for the specific hardware for the customer to fit their needs, both on the latency and on the accuracy, focusing mainly on the computer vision and NLP and on the edge and cloud environments. So building fast and efficient, accurate models is our main business, so to say. So we, at some point, decided to share and bring to the community our findings and show that we can build a foundational model of based on top of the YOLO that is more faster and more accurate than the existing ones. How this talk will be organized. First, quick recap of what YOLO is and how it evolved to this date. What makes the YOLO-NAS different, and what lessons did we learn and we want to share with you today, and how you can quick start using it. YOLO started back in 2016 and made a really long path to this day. It evolved quite significantly, and there were many authors contributing to this. And the success was great since YOLO is simple yet really accurate and really fast and really edge-friendly architecture that you can deploy on various edge devices and as well as the cloud ones. So not a surprise that it's taking over in different cases of the applications compared to faster RCNN, which is way harder to deploy. Perhaps one of the most iconic ones is the YOLO v5 or YOLO v7, v8, which are the most known ones, which are great architectures with great features, great accuracy. But all these models, they are not designed for the specific hardware. And this is important because if you can squeeze 10% more of the model latency without sacrificing any accuracy, then essentially your annual cost of running this model would be 10% less, which is a huge saving. And this is the frontier plot. On the x-axis, you have the latency, essentially the time it takes to get the predictions from the input image. And on the right, you have the accuracy, the mean average precision measured on the COCO data set. So top left is our place where we want to be. It's more accurate and more fast models. So here we showcase what the final result we obtain. We'll talk later how, but important to see that YOLO-NAS, both small m and L variants, provide you better accuracy while being faster than their competitors of the same size. So roughly it's 35% faster, provides 1 point of the AP increase, and it also very quantization friendly, meaning that when you convert your model to the int8 mode, it doesn't lose much of the accuracy. In fact, it loses way less accuracy than other models than if we do quantization for them. This architecture was specifically generated for the NVIDIA T4, which may be not the most up-to-date GPU, but is still a really good choice for doing inference on the cloud, since it's quite cheap, but provides really great value for its price. So we wanted to push the frontier of the fast and accurate detection models, but we also wanted to provide something that we call a foundational model, a pre-trained weights and architecture that is highly suitable for training on any downstream task that you may have. So the idea is that we are showing you how to fine-tune the YOLO-NAS for your specific goal. And we prove that it works quite well. More on this later. One key component of making the YOLO-NAS is the NAS itself. NAS stands for Neural Architecture Search. This is the idea of where one neural network searches the architecture of another one. Perhaps the most prominent example was the Google Inception architecture, where some building blocks were generated by the neural network itself. Then it became clear that we should be generating the new architectures with respect to some limitations or constraints like latency or the accuracy. This is how the efficient net came out. Currently, the trend is to go to the Gen 3 NAS, which includes more advanced features like ability to generate subnets, but we're not going to cover this in this talk. So this is a neural architecture search engine called AutoNAG. Allowed us to take the task, which is object detection, the data characteristics in a nutshell, like how many bounding boxes are, what's their aspect ratio, what's the image size, the information of the target hardware on which you want to run the inference. In our case, it's a T4. And then we run the AutoNAG engine, which builds our search space and try to predict which neural network architecture would be most efficient on this. And the output is essentially the architecture, the final architecture, the PyTorch, in a model that you can train directly and get the final model. So first is the search space. Essentially, it's a huge set of hyperparameters describing how many channels each layer of your neural network should have, what are the activations, what are batch norm, where and how the skip connections should be established. And of course, it could be millions or trillions potential candidates. It's not feasible to train all them in a reasonable manner. Therefore, we apply some prediction model that picks the promising candidates, and on those promising candidates we can run the training to obtain final candidates. In short, the AutoNAG can narrow down search space from 10 to the power of 14 to obtain only 3 final architectures, and overall the whole stage took the GPU time equivalent of training only 5 networks on a full scale. So it's a huge time saving. When we was designing the search space, we wanted our model to be quantization friendly. So we intentionally put building blocks into the model that supports the quantization and doesn't lose any accuracy, which is called the quantization of our rep VGG blocks, more on them later. And we started from design of the YOLO v6 and YOLO v8, which was inspired by their work. And since this architecture was proven to be successful. And once we obtained our 3 final networks, the training process was first to do the pre-training on the Objects 365 dataset, which is way bigger than COCO. So pre-training was a really crucial step to boost the model performance. Then we train it on the COCO, but we also use it pseudo-labeled data that we use it to the COCO dataset, the unannotated part, and we added it to the training regime. And finally, we train it not as standard supervision manner, but we use it the knowledge distillation, where we had 2 models of the same architecture and same size, and we use it knowledge distillation. And all these 3 key ingredients helped us to get model to the best accuracy. Hopefully, there will be a technical report explaining all the steps in the ablation study in the future. Currently, it's not in the progress. And this is a really short animation demonstration showing how this auto-NAG step looked like. So trying different number of channels for the different blocks, different activations, so on, different connections. And we got these points on our accuracy versus latency. And then we get a frontier plot, which is the most efficient models. So on the macro level, the architecture of YOLO-NAS is nothing new. We have a backbone, we have a neck, we have the prediction heads. The backbone is using cross-stage connections like a CSP ResNet or CSP DarkNet. We are using quantization of our RepGD blocks, which is a combination of 3x3 plus 1x1 convolution, which allows efficient fusing at the inference time, which also helps with the inference speed. And we use spatial pyramid pooling at the end of the backbone to capture the global context. Then we pass those intermediate feature layers to the path aggregation network with the bidirectional connections, allowing us to enrich feature map information using top-down and bottom-up approach. And finally, then we do predictions with the detection heads. Okay, we trained the YOLO-NAS. We obtained really good results on the COCO data sets. But is it really good for any other data set? How good is it for the fine-tuning? That's the question we wanted to answer. It appears to be a great collection of the data set, call it Roboflow 100 benchmark. It contains over the 100 diverse data sets over the 7 different categories. Could be biomedical images, some microscopy, plant diseases, MRI, video games, thermal images, night cameras, and more. So, and the rules of this is the simple. You take your model, you train it with the same regime, with the same learning rate, with the same batch size, whatever, on each of those data sets, and you then average your mean average precision for all the data sets. And this gives you a really great estimate how good your model performing on various tasks. So this number is really more trustful than just one MAP score on the COCO. And this is the result. So when we trained YOLO-NAS, we did the fine tuning. We obtained results that outperform all the previous state-of-the-art YOLO models by quite a lot. This is the results per category. This proves our statement that YOLO-NAS is not only a SOTA model on the COCO, but is also really friendly to the fine-tuning, what perhaps the most of the people is looking for. Which is great success, and we are proud to share this model with the community. And is available as a part of the Super Gradients, the open source deep learning training framework from Deci. It is available at github.com Deci.ai Super Gradients. Feel free to try it out right away. We provide pre-trained NAS model, weights, and inference example. Of course, the architecture is there. Of course, there are recipes that allow you to quickly train your YOLO-NAS from scratch. We provide the fine-tuning notebook to help you with that. And of course, Super Gradients provides the advanced training features like mixed precision, exponential moving average, quantization, knowledge distillation to help you get even more better performance of your model. I will answer the question while still didn't get too far away. In the knowledge distillation, how are the teacher networks weight initialized and maintained? So teacher weights, we did the pre-training and training on the COCO using pseudo labels. Those are the fixed teacher weights. So they're not updated anymore. And then during the knowledge distillation, the regular supervision loss and the knowledge distillation loss was applied jointly to the student model. I hope that answered the question. Cool. So on the quick start. So pip install Super Gradients 3.11. And if you are going to just want to see how the model performs, yeah, you can use the predict API, which model.predict, and then you can show whatever you have. Is it an image in an NumPy or pillow, or could be a link, could be a path to the video, whatever we'll figure out. And you can see the result in your Colab or save them to see the locally. I think it's also important to show how to train it. Of course, showing a bunch of code is not that fun on the slides, but I'll do my best to make it easy to digest. So this is the minimal example. Of course, we throw out a lot of the stuff that you still may want to use in your trainings, like configuration files, logging, visualization, whatsoever. But as a bare minimum, you import a bunch of the Super Gradient stuff. You create your experiment and you get the model. Let's imagine for now, we don't use pre-trained weights. We just instantiate the model with 80 classes to match with the COCO number of classes. We instantiate the data loaders. As a Super Gradients, we provide data set implementation for the COCO 2017 to train the YOLO-NAS. We also provide the detection metric, which is minimal precision for you. You don't have to use the PyCoco tools. Our implementation is DDP friendly and works in the PyTorch native tensors. So it's way more easier to throw it in. And here you have it. That's the bare minimum example that would allow you to train the YOLO-NAS. However, I recommend you to look over the recipes and the documentation to learn of the more advanced training features that we offer. So a quick recap of what we learned during the building the YOLO-NAS, that it's important to keep in mind where your model will be running at the inference time, because different devices have different compute features, and TensorRT really can generate efficient architecture for the specific hardware. And if your model design employs those nuances, then you can save a lot of the money on the compute. When doing fine-tuning, it's important to do the head replacement and not to lose any useful weight. So at head replacement, we replace only the classification layer, the last one, convolution, to project embeddings to a specific number of classes, and we keep the size regression part intact, because we observed that on the Roboflow, it was really the key factor to perform well. Also, if you're going to use int8 quantization, it is important that your model to be aware of that and use the quantization aware blocks. And last but not least, nowadays, it's not enough to have just fit predict method. To get the best performance, you have to use advanced training features like EMA, weight averaging, knowledge distillation, in order to obtain the best possible model performance. I see a bunch of the questions, so I'll address them here now. Is narrow architecture search applied only in the backbone or decoder 2? Narrow architecture search was applied everywhere, so on all the model parts. Why YOLO-NAS is considered as YOLO family? Since it highly inspired by the YOLO architecture itself, so it's pretty similar, but still have a different differences. So the training, the format of the predictions, and to some extent even the loss are mimicking the PP YOLO one. So it is fair to say that it stays in the same family. YOLO V8 is licensed with limitation for companies, but yours is Apache 2. Can we use YOLO-NAS without any risk in terms of intellectual property? So YOLO-NAS itself, the model architecture, it is licensed as Apache 2, which means you can use it whatever you like, including commercial ones. However, the weights are licensed as a non-commercial basis, meaning that if you're going to use it in the business, you probably would like to speak to our representative and get the permission to use it. So the model itself is free. The weights are for the non-commercial. What kind of augmentations tried in the training process? Did you consider pre-training with another data set before training with Coco? The augmentations, brightness, contrast change, color augmentations, mix up if I'm not mistaken, and perhaps that's it. We didn't use the multi-scale or mosaic if I'm not mistaken, but we highly encourage you to try out and to let us know about the results. The goal was not to go down the rabbit hole and trying to find the best set of augmentations. I believe it could still allow us to squeeze some more juice from the model, but it's kind of long process to go over the training first on the Object 365, then on Coco, and that was not the goal. Here are the links. I think we will share them afterwards, so you don't have to type them manually, but if you can take a look. The official repository, documentation, the starter notebook, and the Discord community, and you can communicate and ask your questions. Feel free to take a look, give us some stars, and thank you very much for your attention. If there are other questions, I'm happy to answer them.